There are rivers on Mars. Not water, not anymore. There are dry channels and floodplains, and the deltas, where rivers once spilled into standing lakes. All of it still there, carved into the rock, and then frozen in place for 3.5 billion years. Mars had water running on its surface once, and a thicker atmosphere over it, and a warmer world beneath. And then it died. The core cooled, the magnetic field collapsed, the air was stripped away into space and the water went with it, until what was left was the cold red desert that is there now, 60 below across most of the planet, and far colder than that at the poles. We tend to think of Mars as simply a dead place, the way a stone is dead, as though it had always been that way. It was not always that way. Mars is not a world that never lived, it is a world that died, and the question worth sitting with is whether that is the rare exception out here, or the rule. Tonight, we're going to look at what it actually takes for a world to die, and at how many different ways it can happen, starting with the dead worlds right beside us, and working out to the most common worlds in the galaxy. By the end of this, you will understand why being able to hold life is not something a world simply is, but a phase it passes through and then loses. Why the dead worlds pile up far faster than the living ones ever form, and why the earth under your feet is not an exception to any of it, but only early. This is not a story about how rare and precious our world is. It is an honest look at how a living world dies and at the clock that is already running on this one. If the real story of the worlds around us is what you came here for, the kind that does not look away, a like or a subscribe helps more people find the channel, and it means a lot to me. Start with the ground itself. Across the older terrain of Mars, the rock is cut by the shapes that only running water leaves behind. There are valleys that branch the way river systems branch on Earth, narrow at the head and joining into wider channels downstream. There are the flat floors of what were once standing lakes, ringed by the deltas, where sediment piled up as a river slowed and spread into still water. There are minerals in the rock, clays and salts, that only form when water sits in contact with stone for a long time. None of this is subtle, and none of it is in serious doubt. Liquid water flowed across the surface of Mars, filling channels and pooling into lakes before roughly 3.5 billion years ago. To hold that water, Mars needed more than it has now. It needed a thicker atmosphere to keep the pressure and the warmth up, because liquid water cannot survive on a surface where the air is too thin and too cold. Early Mars had that thicker air. The planet beneath it was warmer, wet at least in places, and at least some of the time, a world where a river could run from a highland down into a basin and gather there. That is not the Mars of today. That is a different planet, in the same place, wearing the same name, separated from the present one only by time. Because the planet that is there now is a corpse. The air above the old riverbeds is less than 1% of the pressure at Earth's surface, so thin that liquid water cannot exist in the open at all, boiling and freezing at the same time if you try to pour it out. The average temperature across the planet sits around 60 below. Through the long winters, the poles fall toward 140 below, cold enough to freeze the carbon dioxide out of the air itself and lay it down as frost on the ground. The water that carved the channels is gone from the surface entirely, locked underground as ice or lost to space. What is left is rust-coloured rock, thin cold air, and the dry shapes of a drowned world that has been dead for billions of years. That is the part worth holding on to, because it cuts against the way most of us picture Mars. We tend to think of it as simply a dead place, barren the way the moon is barren, a world that was always a desert and never had a chance at anything else. The surface says otherwise. Mars is not a world that never lived. It is a world that had water and weather and a thicker sky that looked, at least in patches and at least for a while, like somewhere life might have taken hold and then lost all of it, The riverbeds are not a hint that Mars might once have been different. They are the record of it, carved in stone, that the planet ran one way for its first stretch, and a completely different way ever since. There is genuine uncertainty in the details, and it is worth being honest about which parts. The clearest thing is the water. The channels and the lake floors and the water-formed minerals are real, and the case that liquid water flowed there is about as solid as this kind of evidence gets. What is argued over is the climate that held it. The young sun was fainter than the sun is now, which makes a steadily warm and wet early Mars hard to reproduce in the models, and one camp holds that the planet was mostly cold, with water breaking out only in episodes, when something warmed it briefly before it froze again. There is also recent work suggesting that not all of the lost air went to space, that a good fraction of it may have been pulled down into the crust and locked into the rock as the planet aged. The death of Mars is not in question. The exact temperature of its living years and the exact route the air took on its way out still are. Some of these dead waterways have names now, because we have driven machines down into them. There is a crater called Gale near the Martian equator that was once a lake, its floor built up in fine, flat layers of mud, of the kind that only settle out underwater, layers a rover has spent years climbing through and reading, the record of a body of standing water that lasted long enough to lay down stone. There is a basin called Jezero, where a river once emptied into a lake and dropped its load of sediment in a fan-shaped delta, the same structure a river builds where it meets the sea on Earth, and a second machine sits among that deltaic rock now. These are not faint hints, they are lake floors and river deltas, the plain architecture of moving water, sitting dry and frozen on a planet where nothing has flowed for billions of years. And it may have been far more than scattered rivers and lakes. The low, smooth northern third of Mars lies well below the cratered southern highlands, one enormous basin, and a long-running argument holds that it may once have held a sea and ocean across much of a hemisphere, with the line between highland and lowland marking something close to an ancient shore. Whether that ocean was real, and how long it held if it was, is still genuinely debated, because the evidence is old and much reworked since. But the possibility is a serious one, that Mars was not merely damp in patches, but a blue and white world for a time, ocean on one side and ice at the poles, before the long drying took it. Stand on that ground today, and there is nothing of it left to feel. The air is so thin it would not fill your lungs. A trace of mostly carbon dioxide at under 1% of the pressure your body is built for. The cold would take you quickly, 60 below on an ordinary day, the sky a dim butterscotch pink from the fine dust that hangs in the thin air, the light weaker than an overcast afternoon at home, because the sun rides farther off and smaller. There is almost no sound, because there is almost no air to carry it. There is no water, no green, no movement anywhere but the slow drift of dust. It is as quiet and as final as a place can be, and it sits directly on top of the drowned riverbeds of a world that was once something else. It is worth placing that death in time, because 3.5 billion years is not only a large number, it is a specific moment in a story we are part of. When Mars lost its water and its air, the Earth was a very different planet too. There were no plants, no animals, nothing living on land at all. The most advanced life anywhere on Earth was single-celled, microbes in the sea, and the air held little or no oxygen, so Mars did not die in some remote pre-human past with no bearing on us. It died before the Earth itself had done most of its living, while our own world was still a microbial place under a sky nothing would recognize. The two planets were running side by side, both young, both possible, and one of them quietly went out while the other kept going. The cold on Mars now is deep enough to freeze the air itself. Through the long polar winters, the temperature falls so low that carbon dioxide, the main gas in what little atmosphere is left, freezes straight out of the sky and settles onto the ground as white frost, a layer of dry ice laid down over the poles each winter and lifting back into the air each summer. Part of the planet's atmosphere literally falls as frost and then returns season after season on a world too cold to keep all of its air as gas. That is how far Mars has fallen from the world of rivers. The same planet that once had water running across its surface now grows cold enough in places to snow its own air down onto the rock. Mars is not even still, which is one of the stranger things about it. The planet is dead in the sense that matters, no water, no life, no working field, but it still has weather of a kind. Wind moves across it, lifting the fine red dust, and once in a while a dust storm grows until it wraps the entire planet, hiding the whole surface under a haze for weeks at a time. Dunes creep slowly across the floors of the old basins. Frost gathers and lifts at the poles with the seasons. So Mars is not a frozen photograph of a dead world. It is an active one, a thin atmosphere still doing thin atmosphere things, blowing dust around the graves of its rivers. The motion can fool you into thinking something is happening there. Nothing is in the way that counts. It is the idle turning of a world with no water left to run, weather without the one thing that ever made the weather matter. And we have learnt something sharper than water alone from those dead lake beds. The rover climbing through the layers of Gale crater found, in the old lake sediments, the actual chemistry of a habitable place. Not life, but the conditions for it, the right minerals, the chemical ingredients, water that was neither too acid nor too salty, a setting where, by everything we understand, life could have lived if it ever got started. So Mars was not merely wet. For a stretch of its early history it was, by the measures we use, habitable, a world with its window open. Whether anything ever stepped through that open window we do not know, but the window was open and then it closed, which makes Mars not just a world that lost its water, but a world that lost its habitability, the very thing this whole question turns on, already demonstrated once on the planet next door. Some of the channels are far larger than anything water has carved on Earth. There are outflow channels on Mars tens of kilometers wide and hundreds of kilometers long, gouged into the surface by floods so enormous that nothing in recorded Earth history compares. Torrents released all at once when trapped underground water broke loose and tore across the land before freezing or draining away. To cut features that size takes water in volumes hard to set against anything familiar, moving fast across a whole region of the planet. Those floods happened, and then they stopped, and the dry scars are still there, far too big to miss, carved by an amount of water the Mars of today could not produce if every scrap of its remaining ice melted at once. The size of the channels is its own measure of how much the planet has lost. So we have a world that lived and then died, sitting right next door, close enough that we have driven machines across the floors of its dead lakes. The question that should follow is not whether Mars died, because the ground settles that. The question is whether Mars was simply unlucky, a single planet that drew a bad hand, or whether it died in one of the ordinary ways that worlds die, a way that says something about every world, including this one. To answer that, you have to stop looking at the riverbeds and start looking at what actually killed the planet that made them. Mars died from the inside out, and the reason it died is something it could never have changed. It was too small. Mars is about half the diameter of Earth and carries only around 1/10 of Earth's mass, and that size, more than its distance from the Sun, is what sealed its fate. A small world cannot hold its internal heat the way a large one can, and on a rocky planet the internal heat is not a detail. It is the engine that runs everything that keeps the surface alive. Deep in its early history, Mars was hot inside, hot enough that its core was molten and moving. A churning core of liquid metal does something for a planet that nothing else can, and the effect is purely physical. The motion of the metal generates a magnetic field, a global one, that wraps the entire planet from pole to pole. Earth has exactly this, driven by exactly this, a molten outer core in constant motion, throwing up a field that reaches far out beyond the atmosphere. That field is a shield. It stands between the planet and the sun, and it matters more than almost anything else for whether a world keeps its air. Being small, Mars cooled fast. A large hot object holds its heat for a long time, while a small one sheds it quickly, the same way a small cup of coffee goes cold long before a full pot. The interior of Mars lost its heat to space across its first several 100 million years. The churning in the core slowed, and around 4 billion years ago it stopped. When the motion stopped, the dynamo died, and when the dynamo died, the global magnetic field collapsed. The shield came down, and once it was down, the planet lay open to the sun. The sun does not only shine, it blows. A steady stream of charged particles pours off it in every direction, at hundreds of kilometers a second, the solar wind, and when that wind reaches a planet with a magnetic field, the field turns it aside. With the field gone, the solar wind struck the top of the Martian atmosphere directly, and it began to strip it away. The particles slam into the upper air and knock gas molecules loose, fast enough to throw them clear of the planet entirely, out into space where they never come back. It is a slow erosion, a sandblasting that works one thin layer at a time, and spacecraft in orbit around Mars still measure it happening today, carrying off the remains of the air at around 100 grams every second. When the sun was young and far more violent, that rate would have been many times higher. As the air thinned, the water followed it. Liquid water needs the pressure and the warmth that a thick atmosphere provides, and as the atmosphere bled away, the surface conditions crossed the line past which water cannot stay liquid. Some of it froze into the ground, where a great deal of it still sits as buried ice. Some of it broke apart in the thin upper air and escaped after the gas. The rivers stopped running, the lakes dried or froze, and the planet settled into the cold, dead state it has held ever since. The chain ran in a clear order, each step forcing the next. A small world, a fast cooling core, a dead dynamo, a collapsed field, an exposed atmosphere, stripped air, vanished water, a dead planet. The exact timing is not pinned down, and that uncertainty is real. The shutdown of the dynamo is usually placed somewhere between about 4.2 and 3.7 billion years ago, which is a spread of 500 million years, and recent work reading the faint magnetism still frozen into the oldest Martian rock argues that the field may have lasted longer than the simple story says, and behaved in a more complicated way while it did. There is even a finding that a weak, patchy field, the kind a dying dynamo would produce on its way out, might strip an atmosphere faster than no field at all, by channeling the solar wind down onto the planet, rather than turning it cleanly aside. The picture is not perfectly clean, but the shape of it holds. Mars cooled, lost its field, and lost its air because it was small. Earth runs the same engine Mars lost, and it is a large part of why you are breathing. Deep inside this planet, under thousands of kilometers of rock, there is a core of iron and nickel, its outer layer molten and in constant motion, and that moving metal throws up a magnetic field that reaches far past the top of the atmosphere. You cannot see it, but it is the thing that turns the solar wind aside, the reason the same stream of particles that scoured Mars bare slides around Earth, instead of stripping it away. The lights that show near the poles are the edge of it, the places where a little of the solar wind leaks through and strikes the air. Earth is larger than Mars, and has held its internal heat far longer, so the engine is still turning, the field is still up, and the air is still here. The gap between a living Earth and a dead Mars is in large part the gap between a core still molten and a core gone still. The death of the Martian field did not erase itself. Frozen into the oldest crust of Mars are stripes of faint magnetism, locked into the rock as it cooled while the global field still ran, a fossil of a shield that no longer exists. They sit there in the southern highlands, the memory of a field held in stone, while above them the solar wind still does its slow work on what little air remains, lifting gas from the top of the atmosphere, charging it, and flinging it out into space at around 100 grams every second. The shield is a fossil. The stripping is still live. Mars is showing us both halves of its own death at once, the cause set into the rock, and the effect still going on in the sky. The hard part of this is that the size of a world is set at its birth and cannot be changed, which means the death is in a sense decided from the start. A world is built from whatever material gathers in its part of the disk around a young star, and that fixes its mass, and its mass largely fixes how long it can hold the internal heat that runs its field and its weather. A small world like Mars is born with too little to work with. It will cool and lose its field and shed its air no matter what happens on its surface, given enough time, because the clock on its internal heat started running the moment it formed and was always going to run out early. Mars was not killed by some accident partway through its life. It was built too small to last, and the dying simply followed from that, on schedule. Earth holds on partly because it does something Mars could not keep doing. The surface of Earth is broken into plates that move, sliding and diving beneath one another, dragging surface rock down into the hot interior and bringing fresh rock up, a slow churning of the whole outer planet. That churning helps Earth shed its internal heat steadily and keeps running the carbon cycle that feeds the thermostat. Mars, smaller and cooler, locked up early into a single rigid shell with no plates moving at all, which let its interior stagnate and its surface go static. A world that cannot turn itself over slowly loses the processes that keep it alive. Earth is still turning itself over. Mars stopped long ago, and a planet that stops is a planet on its way to dead. And small worlds are not the exception. They are the common kind. When rocky planets form, the small ones outnumber the large by a wide margin. The same way there are far more pebbles than boulders on a beach, because it takes a great deal of gathered material to build something Earth-sized, and only a little to build something Mars-sized or smaller. So the death that took Mars, the slow cooling, and the lost field and the stripped air, is not a rare misfortune that struck one unlucky planet. It is the likely fate of the most numerous kind of rocky world there is. Across the galaxy, the small worlds, the ones too light to hold their heat, are everywhere, and most of them will cool and lose their fields and shed their air if they have not already, each one running the same sequence Mars ran and ending the same way Mars ended. The lesson under the Martian death is that a planet's atmosphere is not something it keeps automatically. It is held against constant loss, defended by a magnetic field that is itself powered by a hot churning interior, and the moment that defense fails, the loss begins. Earth's air is not simply sitting on the planet by right, it is being actively protected every second by the field thrown up from the molten core, and it would begin to go the way of Mars if that engine ever stilled. We do not think of the ground we stand on as something held in place by a dynamo deep underfoot, but it is, and the dead air of Mars is the demonstration of what the failure looks like. An atmosphere is not a state a world rests in, it is a balance a world maintains until it cannot. And that is the part that should make you sit up, because being small is not a flaw unique to Mars, it is just a size. The death that took Mars is waiting for any rocky world that cannot hold its internal heat long enough, which raises the obvious next question. A larger world, one with enough mass to stay hot inside and keep its field running, ought to be safe from this particular death. Earth's other neighbour is almost exactly Earth's size, with no shortage of internal heat, and a thick atmosphere it has never lost. By this logic, it should be the success story Mars never managed to be. It is instead the most thoroughly dead world in the solar system. Venus should have worked. It is almost exactly the size of Earth, nearly the same mass, the same kind of rock, built in the same part of the same disk of material, around the same star. It is not small, so it never had the Martian problem of a core gone cold and a shield brought down. It kept its heat, kept its thick atmosphere, and has more air over it than Earth does by far. By every measure that killed Mars, Venus should have been fine, and Venus is the closest thing to a furnace that a solid planet can be. The surface of Venus sits at about 465 degrees, hot enough to melt lead, hot enough that a sheet of it, laid on the ground, would puddle. The atmosphere is almost entirely carbon dioxide, and there is so much of it that the pressure at the surface is around 92 times the pressure at sea level on Earth, the kind of crushing weight you would meet only if you sank nearly a kilometre under the ocean. Above all of it hang permanent clouds, not of water, but of sulfuric acid. There is no liquid water anywhere on the planet, not a drop, not a trace pooled in any low place. Venus is a dry, crushed, poisoned oven, and it has been one for a very long time. It was probably not always like this, and the evidence for that is still in the air. When the water on a planet is broken apart and lost to space, the lighter kind of hydrogen escapes more easily than the heavier kind. So a world that has lost an ocean is left with air enriched in the heavy form, a chemical fingerprint of water that used to be there. Venus carries that fingerprint strongly. Its atmosphere is rich in heavy hydrogen, which points to a great deal of water that the planet once had and no longer does. The models that try to account for it suggest Venus may once have held enough water to wrap the whole surface in an ocean, possibly kilometers deep. The twin of Earth may have started with seas of its own. What happened to them is the second way a world dies, and it is the opposite of what took Mars. Venus orbits closer to the Sun, and it takes in more sunlight as a result, and at some point the heat pushed the planet past a threshold that runs away from itself. Water vapor is a powerful heat-trapping gas, more so than carbon dioxide. So when a warm ocean puts more vapor into the air, that vapor traps more heat, which warms the ocean further, which lifts still more vapor into the air, which traps still more heat. Once that loop takes hold above a certain point, nothing stops it. The oceans evaporate completely into the sky, the surface bakes, and the water vapor rises to the top of the atmosphere, where sunlight breaks it apart, and the hydrogen escapes to space for good. The planet does not just lose its oceans, it loses the very possibility of having them permanently, because the water itself is gone. This is the runaway greenhouse, and Venus is what one looks like when it has finished. The numbers around the threshold are the part that should unsettle you. The greenhouse warming on Venus, the amount its atmosphere heats the surface above what bare sunlight would do, is around 500 degrees. On Earth, the same effect, the same kind of physics, raises the surface by about 33 degrees, which is the comfortable difference between the frozen rock Earth would otherwise be and the temperate world it is. The difference between 33 and 500 is not a difference of kind. It is the same process, the same gases, run to its limit, and the runaway can begin at only about 1.1 times the sunlight Earth receives right now. That is the margin. A world like ours, getting a tenth more light than we get, can tip into the process that emptied Venus. There is honest uncertainty here too, mostly about the timing. Whether Venus held stable oceans for a stretch of its history and then lost them, or whether it was always too close and too hot for the water to settle into oceans in the first place, evaporating before it could ever pool, is still argued. Either way, the present is not in dispute. The water is gone, the surface is hot enough to melt metal, the air is acid and crushing, and the runaway greenhouse is the accepted reason a world that should have been Earth's twin is the deadest place we know. We know what the surface is like because we have landed on it, briefly. Machines built to survive the descent reached the ground and sent data back, and then the heat and the pressure killed them within about 2 hours, every one of them, because nothing we have built can last down there. The pressure alone would crush most structures, 92 times the weight of the air you carry now, a force found on Earth only deep beneath the ocean. The heat does not merely kill a body, it cooks electronics, softens metal, defeats every seal. There is no standing on Venus the way you might stand on Mars in the right suit. The planet destroys whatever touches its surface, quickly, and then carries on exactly as it has for billions of years. And there is no coming back from it, which is what makes the runaway greenhouse so final. Once the oceans have boiled into the sky, and the water vapor has carried the planet's hydrogen up to where sunlight can break it apart and let it slip away, the water is not stored somewhere, waiting to return. It is gone from the planet entirely, lost to space, and a world cannot build an ocean out of nothing. The door swings only one way. A planet that merely cools after a warm spell can recover, but a planet that has lost its water to a runaway has lost the raw material of every ocean it could ever have had, for good. Venus did not simply get hot, it used up its water, and a world with no water does not get a second chance at being alive. The thing to hold about Venus is that it is not an alien world built on different rules. It is what Earth could become, running the same physics, a little hotter. The two planets are nearly the same size, the same rough makeup, formed at the same time from the same material, around the same star. Close enough that early on they may have looked like siblings, both warm, both wet, both promising. The difference was a matter of degree, a little more sunlight on Venus, a threshold crossed, and the feedback did the rest. There is no special ingredient that made Venus die and spared Earth. There is only the position in the band and the brightening of the sun, and as the sun brightens, Earth edges toward the same threshold Venus already crossed. Venus is not a warning about some far-off exotic danger. It is a picture of the same death Earth is slowly moving toward, already finished, next door. And Venus turns so slowly that its day is longer than its year, the planet creeping around on its axis so sluggishly that the sun, if you could see it through the acid clouds, would take months to cross the sky. There is no quick cycle of day and night to break the heat, no cool side that ever gets relief. The thick atmosphere spreads the warmth so evenly that the night side is nearly as hot as the day side, the whole planet baked to the same lethal temperature top to bottom and pole to pole. It is not a world with hot places and cooler places where something might hide. It is uniformly, completely hostile, a single temperature of death laid across the entire surface, and it has held that way without relief for longer than the Earth has had complex life. What unsettles me most about Venus is how little separated it from Earth. The two were not dealt wildly different hands. Venus sits about a third closer to the sun and takes in not quite twice the sunlight, and that was enough over time to push it across a line that Earth has so far stayed behind. There was no catastrophe, no great impact, no special curse laid on Venus. The same processes that keep Earth temperate ran a little hotter there and tipped into the runaway, while here they have held, so far. It is a knife edge, and we are on the living side of it, largely because of where we happen to form and how the sun has brightened, not because Earth is built of sturdier stuff. The line between a living world and a dead one can be that thin, a third of the distance to a star, a single threshold crossed, and everything on the far side of it different. That heavy hydrogen in the air of Venus is worth pausing on because it is the clearest fingerprint of the vanished water. Ordinary water is built with light hydrogen, but a small fraction of any water carries a heavier version of the atom instead. When sunlight breaks water apart at the top of an atmosphere and the hydrogen escapes to space, the light kind escapes more readily and the heavy kind lags behind. So a world that has boiled off and lost an ocean is left with air enriched in the heavy form, far above the ratio its water began with. Venus shows exactly that enrichment, and strongly. The air itself carries the chemical signature of seas that are no longer there. The leftover trace of water that rose into the sky came apart and drained away into space, written into what remains. The oceans are gone, but they left their mark in the proportions of the air. From here, Venus is the brightest thing in the sky after the sun and the moon, the brilliant point people have called the morning star and the evening star for as long as there have been people to look up. That brightness is the acid clouds, a complete white shell wrapped around the planet, throwing back most of the sunlight that strikes it. The thing that makes Venus shine so beautifully from a distance is the same thing that seals the heat against its surface and hides the dead world underneath. We have been admiring the top of a sealed furnace, mistaking the glare off its lid for the gleam of a bright companion world. The loveliest point of light in the night is the reflective roof of the deadest place we know. So now there are two deaths on the table, and they sit on opposite sides of Earth in more than one sense. One neighbour was too small, lost its heat, lost its shield, and froze. The other was the right size, kept everything Mars lost, and burned anyway. Earth sits between them, the same age, built from the same material, neither frozen nor baked, holding water on its surface across billions of years. The comforting way to read that is that Earth landed in the safe middle, far enough from both deaths to be secure. The honest question is how wide that safe middle really is, and whether sitting in it now means sitting in it for good. The safe middle is narrower than it feels, and it does not stay where it is. Around any star there is a band of distances where a world can hold liquid water on its surface, close enough that it does not all freeze, far enough that it does not all boil. We call it the habitable zone, and the name makes it sound generous, a comfortable region a planet can settle into. It is not generous, it is a thin shell, and its edges are exactly the two deaths we have already seen. Past the outer edge, the warmth runs short and the water freezes, which is the cold death that took Mars once its thin air could no longer hold any heat. Inside the inner edge, the sunlight is strong enough to start the runaway, and the water boils away into the sky, which is the hot death that took Venus. The zone is the gap between those two edges, and for the Sun that gap is not wide. The inner edge, the line past which a world begins to run away into a greenhouse, sits only about a tenth more sunlight inward from where Earth orbits now. Earth is not sitting comfortably in the centre of a broad, safe region. It is sitting fairly close to the hot edge of a narrow one. But the width is not even the most important part. The real problem is that the band does not hold still. Stars do not burn at a steady brightness across their lives. They brighten, slowly and relentlessly, as they age and the physics of their cores shifts, and the Sun is no exception. It is brighter now than it was when Earth formed, and it will be brighter still in the future, on the order of 10% brighter every billion years or so. As a star brightens, the whole habitable zone moves outward, because the distance where water can survive gets pushed farther from a stronger source of heat. The cold edge moves out, the hot inner edge moves out. The entire band slides away from the star over time. A planet cannot follow it. A world holds the orbit it has, fixed by gravity and momentum, and it does not drift outward to stay in the comfortable zone as the zone retreats. So what actually happens is that the band slides outward and leaves the planet behind, and the planet, sitting still, finds the dangerous inner edge creeping toward it from the inside. A world that begins comfortably in the middle of the zone will, given enough time, find itself near the inner edge, then at it, then past it, as the moving band abandons it to the growing heat. The planet did nothing wrong and changed nothing about itself. The ground under the definition of safe simply moved. This is why being in the habitable zone today is not a guarantee of anything except today. It is a snapshot of a moving situation, a photograph of a planet that happens right now to be inside a band that is sliding toward the star relative to it. Venus, almost certainly, was inside the habitable zone early in the solar system's history, when the sun was fainter and the inner edge sat closer in. The sun brightened, the inner edge swept outward past Venus, and Venus was left on the hot side of it, where the runaway finished the job. Venus is not a world that formed in the wrong place. It is, in part, a world that the moving zone walked away from. There is real disagreement about exactly where the edges of the zone fall, and it is worth saying so plainly. Clouds can cool a planet by reflecting sunlight back to space, or warm it by trapping heat, and depending on how they behave, the edges shift. The composition of the atmosphere moves them too. So different models draw the inner and outer edges in somewhat different places, and the precise width of the safe band is genuinely unsettled. What no model disputes is the part that matters here. The band is finite, with a hot edge and a cold edge, and it migrates outward as the star ages. The argument is over the exact lines, not over whether the lines exist and move. You can read the two edges of the band straight off our own solar system. Closest to the sun is Mercury, a small scorched world with no real air, baking on its day side, a planet so near the fire that no atmosphere and no water could ever have held there. That is the inside of the inner edge. Far out past Mars lie the cold worlds, the moons of the outer planets locked in deep freeze, places with water in plenty but only as rock-hard ice, because the sun out there is a bright point and little more, far too weak to melt anything. That is the outside of the outer edge. Between the scorched inner worlds and the frozen outer ones, the band where water can stay liquid is a thin ring, and only Earth sits cleanly within it. Mars rides the cold edge of it. Venus fell off the hot edge. And the band that truly matters is thinner still, because a world has to stay in the safe zone not for a moment, but for the billions of years that life takes to begin and hold on. The band where water can sit today is one thing, the narrower band where a world can stay safe across the whole long stretch life needs, while the star brightens and the edges march steadily outward, is much tighter than that. A planet can sit comfortably in the zone right now and still be doomed if the brightening sun will push the inner edge past it before its window has fully run. Earth sits close enough to that inner edge that, over the long run, it does not stay on the safe side of it. The band we live in is not only thin, we are already near the dangerous side of it. Earth's position in the band is less comfortable than it looks from here. We tend to picture our planet sitting safely in the middle of the safe zone, but by the measures that account for the brightening sun, Earth is closer to the hot inner edge than to the cold outer one, and drifting the wrong way as the sun strengthens. The planet is not centered in its window. It is in the inner part of it, with the runaway edge ahead and slowly closing. This is part of why the end comes in roughly 1 billion years rather than many billions. We are not going to be gently nudged out the far cold side of the zone in some distant future. We are going to be pushed off the near hot edge, the same edge Venus fell from, and we sit on the warm side of the band to begin with. The far side of the band is its own kind of graveyard, and the outer solar system is full of it. Beyond Mars, the worlds are cold all the way down, the large moons of the giant planets wrapped in ice kilometers thick, with oceans of liquid water sealed under frozen crusts in a few of them, kept liquid not by the distant sun, but by the squeezing and flexing of tides. Out there, the sun is too weak to matter for warmth, a bright star rather than a source of heat, and any world that drifted past the cold edge of the band would freeze its surface solid and hold it that way. A world does not need to burn to die. It can simply fall on the cold side of the line and lock into ice, the way Mars did once its air grew too thin to hold any warmth at all. Both edges kill. They only kill in opposite directions. This is the thing to keep in mind whenever you hear that another habitable zone world has been found. The phrase sounds like a promise, a place where life could be comfortable, But all it really means is that a planet sits, at this moment, somewhere in the thin band where liquid water is possible, given the right air. It says nothing about whether the world kept that air, whether it is locked to a flaring star, whether its window has already closed or never opened in the first place. Being in the habitable zone is a statement about a distance, not about a world being alive or even able to be. Most of the worlds that have ever sat in a habitable zone are dead now, because sitting in the band is the beginning of the question, not the answer to it. The headline names a location. It does not name a living world. You can watch the band move just by looking back along Earth's own history. When the sun was young, it was something like a third fainter than it is now, which means the whole habitable zone sat closer in, and Earth in the same orbit it holds today was nearer the cold outer part of the band than the warm middle. As the sun has brightened across 4 billion years, the band has slid outward, and Earth is in effect drifted across it from the cooler side toward the warmer, without ever changing its orbit at all. We are not where we started within the band, not because we moved, but because the band moved under us. And it keeps moving in the same direction toward the day the hot inner edge reaches Earth and passes it, the way it long ago reached and passed Venus. Put the two facts together, the thinness and the motion, and the safe band starts to look less like a region and more like a passing window of its own. A world does not simply get to be in the habitable zone, it gets to be in it for a while, as the band sweeps slowly outward and the world holds still, in range for a stretch and then left behind. The habitable zone is itself a kind of moving window in space. The same way, the habitable lifetime is a window in time, and they are really two views of the one fact. There is a span during which a given distance from a given star is safe, and that span ends because the star will not stay the brightness that made the distance safe. Nothing about a world's place in the band is permanent. It is only current. So the safe middle is thin, and it is sliding toward the inner edge relative to any world that sits in it, which means no world stays inside it forever. Sooner or later, the band moves on and the heat closes in. That turns the comfortable idea of a habitable world into something with a deadline attached, and it raises the question that the rest of this comes down to. If no world holds its place in the safe band permanently, then how long does any world actually get? How long is the window between the day a world becomes able to hold life and the day it loses that ability for good? Here is the shift that changes how all of this looks. Being able to hold life is not a property a world has. It is a phase a world passes through, bracketed by two deadlines, and the phase is short compared with how long the world itself exists. We talk about habitable worlds as though habitable were a fixed label, a category a planet belongs to, like its mass or its colour. It is not. It is a stage with a beginning and an end, and almost everything about when that stage starts and stops is set by physics that has nothing to do with whether anything is alive. The window opens when a world has settled. A freshly formed planet is a hostile place, molten or bombarded or wrapped in the wrong kind of air, and it takes time, often hundreds of millions of years, before the surface cools and steadies into something where liquid water can sit and chemistry can run slow and stable. That is the front edge of the window, the point where a world becomes the kind of place life could get a footing. It is not guaranteed to arrive, and on many worlds it never does, but where it does arrive, it marks the opening. The window closes from the other side, and the thing that closes it is usually the star. A small world can close its own window by cooling from within and freezing, the way Mars did when its internal heat ran out. But the more common and more certain ending comes from the star itself, brightening with age until it pushes the inner edge of the habitable zone outward, past the planet, and tips it into the runaway, the way Venus was pushed. The same star that warmed the world into life is the thing that eventually cooks it out of it. The star lights the window and the star slams it shut. It is both the source and the executioner. And there is no appeal, because a star brightening as it ages is not a malfunction. It is simply what stars do as they burn. Between those two deadlines is the habitable lifetime, the span a given world actually gets, and measured against the life of the star it is brief. The sun will burn as a stable star for around 10 billion years. The stretch of that during which Earth can hold liquid water and a living surface is only a few billion, a fraction of the whole. For most of the sun's life, Earth will either not yet have been ready or will already be cooked. The living window is a slice in the middle, not the whole loaf. And that is true not just for Earth, but for any world around any star. The window is always a portion of the star's life, never the entirety of it, and often a small portion. What makes this feel different from an ordinary fact about astronomy is that it applies to everything, with no exceptions carved out for the worlds we would most want to last. There is no kind of planet that gets to skip the closing of its window. A world either has not yet entered its habitable phase, is in it now, or has already left it, dead. Every world that has ever held life falls into one of those three states, and two of the three are forms of not being alive. The living phase is the narrow middle of a sequence that runs, on every world, toward an end. The honest complication is that the exact length of any one window is hard to predict, because it depends on details we cannot fully pin down. The thickness and makeup of the atmosphere, the way clouds and ice and rock feed back on the temperature, the slow churn of carbon between the air and the stone, all of it nudges the window longer or shorter. There is even reason to think luck plays a part. Simulations that run the same planet many times over, with the climate feedback set slightly differently each time, find that staying habitable for 3 or 4 billion years the way Earth has is not the typical outcome but one of the better ones, with loss of habitability somewhere along the way looking more likely than not. Earth keeping its footing this long may be partly a matter of having drawn a good run, not a guarantee that was always going to hold. The strange thing is that Earth should have frozen early and did not, and the reason it did not is the same reason it will eventually cook. When the sun was young, it was noticeably fainter, putting out perhaps a quarter less energy than it does now, weak enough that Earth's oceans ought to have frozen solid for much of their early history. They did not, and the leading explanation is a slow natural thermostat built into the rock and the air of the planet. Carbon dioxide leaks out of the interior through volcanoes, and is drawn back down as it reacts with rock and washes into the sea, and the balance between the two shifts with temperature in a way that pushes back toward warmth whenever the planet cools. Early on, with a faint sun, that thermostat kept more carbon dioxide in the air and held Earth warm enough for liquid water to stay. But the thermostat works only by adjusting how much carbon dioxide is in the air, and there is only so far it can go. As the sun brightens across billions of years, the thermostat compensates by drawing the carbon dioxide down, lower and lower, to hold the temperature in check. The trouble is that there is a flaw. Plants need a certain amount of carbon dioxide to run the chemistry that keeps them alive, and once the thermostat has pulled it down near that flaw, there is no more room left to compensate. After that, the brightening sun wins outright, the temperature climbs without check, and the slow drawdown that kept Earth livable for billions of years becomes the very thing that ends it. The mechanism that bought all of Earth's time is now most of the way to the bottom of what it can do. The window has a beginning as well as an end, and the beginning is easy to forget. The early Earth was not habitable in any sense that would have helped a complex creature. For its first stretch, it was struck heavily by leftover debris from the forming solar system, hit hard enough at times to boil parts of the ocean and sterilize the surface, and it took hundreds of millions of years for that bombardment to ease and the surface to settle into something stable. Only then did the window really open. So the few billion years Earth has had as a living world are bracketed on both sides, opened late after a violent start and closing early under a brightening sun, a stable stretch carved out of a planet's life that was hostile before it and will be hostile after it. Set that living window against the whole life of the planet, and it is a slice in the middle, not the bulk of it. Earth will exist as a body in some form for many billions of years, first as a living world, then as a sterile one, then as whatever the red giant sun leaves behind. The stretch during which it can hold a living surface is only a portion of that, bracketed front and back by lifelessness. And the stretch during which it can hold complex life, the breathing animal world, is narrower again, a thin band inside the already thin band of bare habitability. We exist in the narrowest part of a narrow window, on a world that is mostly, across its whole existence, going to be dead. That is not a gloomy way of putting it. It is only the proportion measured out honestly. And there is no negotiating with any of this, which is part of what makes it land the way it does. The clock on a world is not set by anything the world does, or anything that lives on it. It is set by the size the planet was born with, and the star it happens to orbit, by physics that was running long before any life appeared, and will go on running long after. A living world cannot brighten its star more slowly, cannot widen its band, cannot hold its window open by being clever or careful. The processes that grant the window, and the processes that close it, are completely indifferent to whether anyone is home. The window is a gift nobody gave, and a sentence nobody passed, only the way the numbers happen to fall for a particular world around a particular star, and the world rides it out either way. And the size of the window depends heavily on the kind of star, in a way that cuts against the brightest ones. Large, hot stars burn fast and die young, some lasting only a few million years before they exhaust themselves and explode. Far too short a time for a world around them to settle, let alone grow anything. The middle-sized stars like the Sun get billions of years, enough for a real window if a world sits in the right place. The small red dwarfs get the longest runs of all, tens of billions of years, though their worlds face the locking and the flares. So the windows are not handed out evenly. The hottest stars offer almost no time, the sun-like stars offer a real but finite stretch, and the most common small stars offer enormous time under the hardest conditions. The clock runs at a different speed around every kind of star, but it always runs, and on the bright, fast stars it barely starts before it stops. And the window many worlds get is no window at all, because the front edge never arrives. Plenty of worlds never settle into stable conditions in the first place. Too battered, too small, too close, too far, their surfaces never holding still long enough for the chemistry of life to even begin. For those worlds there is no opening to speak of, only the long lifelessness before running straight into the long lifelessness after, with no lit stretch in between. So when we count windows, we are already counting the lucky cases, the worlds that at least manage to open the door. A great many worlds never get that far. The window is not only brief where it happens, it fails to happen at all on most of the worlds that might, in principle, have had one. So every world gets a clock, set mostly by its size and its star, running down toward an end it cannot avoid. That is unsettling enough as a statement about distant planets. It becomes something else when you turn it on the world you are standing on, because the clock on Earth is not some far-off thing waiting quietly in the future. It is already running. It has been running the whole time, and when you look at where the hands actually sit, most of the time has already gone. Earth is not the exception. It is one more world inside its window, and most of that window is already behind it. We have been habitable for around 4 billion years, which sounds like a beginning, the long, secure foundation of a world just getting started. It is closer to the opposite. Earth's total run as a living world is on the order of 5 billion years, maybe a little more, which means we are not near the start of the story. We are something like 3/4 or more of the way through it, far closer to the end of the window than to its opening. And the first stage of the ending is nearer than almost anyone assumes. The oxygen in the air, the gas that makes complex life possible, the thing every breathing creature on the planet depends on, is not a permanent feature of Earth. It is projected to last only about another billion years before it collapses. As the sun brightens, the slow chemistry that governs how much carbon dioxide stays in the air draws that carbon dioxide steadily down, and below a certain point, the plants that produce oxygen can no longer run their chemistry and begin to fail. Once the producers go, the oxygen follows, not gradually over the remaining life of the planet, but in a relatively sharp fall, dropping the air back toward the low oxygen, high methane state Earth had in its first couple of billion years, before complex life existed at all. The ozone layer, which is made of oxygen and shields the surface from the sun's harder radiation, goes down with it. Earth will become, once again, a world of microbes in a hazy orange sky, and it will spend the rest of its habitable time that way. Put against the whole window, oxygen turns out to be a brief chapter, not the settled condition of the planet. Breathable air will have been present for only around a third of Earth's total habitable lifespan. The world that we think of as normal, the green and breathing one, is the unusual stretch bracketed before by billions of years without oxygen, and after by billions more without it again. We happen to be alive inside the oxygen window, which is itself only part of the habitable window, which is itself only part of the life of the planet. We are living in the narrow-lit middle of a narrow-lit middle, and calling it the permanent state of things. After the oxygen goes, the longer clock keeps running. As the sun continues to brighten, the surface keeps warming, and once the sun is roughly 10% brighter than it is now, Earth crosses into the same process that emptied Venus. The oceans begin to evaporate in earnest, water vapor floods the upper atmosphere, sunlight breaks it apart, and the hydrogen escapes to space. The water that has covered most of this planet for billions of years bleeds away into the sky and is gone. What is left after that is a hot, dry, sterile world. The oceans reduced to empty basins, the air thick and strange, the surface scorched under a sun that has grown too strong. The same ending Venus reached, arrived at by the same road, only later. It helps to set the number against something you can feel, because a billion years means nothing on its own. The last time Earth was a billion years from where it is now. Looking the other way into the past, oxygen was only beginning to gather in the air, and nothing more complicated than single cells existed anywhere on the planet. Every animal, every plant, every forest and reef and herd, the whole history of complex life on Earth, fits inside that same span of time going forward. So when the models say the breathable air has about a billion years left, they are saying it's roughly one more run of the entire age of complex life, and then it is over. That is not a comfortable distance. It is the same clock that already produced everything, with one turn left. The mechanism behind the collapse is worth seeing clearly, because it ties the breathing air directly to the brightening sun. Almost all the oxygen in the air is put there by life, by organisms that take in carbon dioxide and sunlight, and give off oxygen as the byproduct. They need the carbon dioxide to do it. But the same thermostat that has kept Earth cool against the brightening sun works by pulling carbon dioxide out of the air, and as the sun keeps strengthening, that drawdown has to go on, forcing the carbon dioxide lower and lower. At some point it crosses below what the oxygen makers need to function. When they fail, the source of the oxygen fails with them, and the oxygen already in the air is used up and bound back into rock and not replaced. The air does not slowly thin. It tips once the producers cross their limit and falls. What replaces it is the kind of air Earth had through its first couple of billion years before oxygen ever built up. Methane gathers instead, hazing the sky toward orange. The ozone layer, which is made of oxygen and which now blocks the sun's harder ultraviolet light, thins and vanishes along with the oxygen that formed it, and the surface below is left open to radiation the breathing world is shielded from. The complex life that depends on oxygen, which is to say nearly everything you would recognize as alive, cannot survive it. What remains for the long stretch afterward is a world of microbes again, the simple low oxygen life that ran the planet through its first half, and will run it again at the end, under an orange sky, on a surface no animal could endure. And that is still not the end of the road, only the end of the living part of it. Long after the oceans have boiled away and the surface has gone sterile, the sun itself will keep aging, and in something like 5 billion years it will swell into a red giant, ballooning outward as it burns through its core, growing large enough to swallow the inner planets. Mercury and Venus will almost certainly be engulfed. Earth may be drawn in as well, or may be left as a scorched cinder circling just outside the bloated star. Either way, by then, the question of life on Earth will be billions of years settled. The planet will have been dead far longer than it was ever alive, a burnt remnant orbiting a dying star, the green moment a thin forgotten layer somewhere deep in its rock. Look the other way down the same clock and the scale of what is at stake comes clear. Complex life, the kind that builds bodies out of many cells, is recent on Earth, only the last several 100 million years of a history more than 4 billion years long. For something like 9/10 of the time Earth has been alive, the most advanced thing on it was single-celled. Everything you would call a creature, every animal that has ever lived, fits inside that recent sliver. So when the air is projected to fail in about 1 billion years, it is worth seeing that the entire age of complex life so far is roughly the same length as the time complex life has left. We are not at the dawn of the animal world with endless time ahead of us. We are somewhere past its midpoint, with the back edge of the window already in view. I want to be careful not to overstate the nearness of this, because 1 billion years is not a human concern in any direct way. No person, no civilization, nothing on the timescales we actually live and plan within, will feel the brightening sun or the failing air. The dangers that matter to us are far closer and far faster, and none of them are this. But the point of looking at the billion-year clock is not to worry you about it. It is to place the Earth honestly, to see that even the thing we treat as the most permanent fact there is, a living, breathing world, is a temporary condition with an end already written into the physics. The nearness is not the point, the certainty is. It changes something about the idea of home to know this. We tend to feel that Earth is the place life belongs, the natural and permanent setting for it, with the dead worlds as the exceptions that went wrong somewhere. The clock says it is the other way round. Earth is the temporary setting, the brief exception, and the dead worlds are the rule that Earth is on its way to joining. The breathing world is not the baseline that the universe departs from in those barren places. The barren places are the baseline, and the breathing world is the departure, the rare lit interval that does not last. Home, in the deepest sense, is not a permanent address. It is a window that happens to be open right now, on a world that has held it open longer than most, and will not hold it open forever. And of all the ways the window closes, the loss of the breathing air is the one that reaches me most directly, because it is such an ordinary thing to lose. Not a distant catastrophe, not the sun swelling billions of years out, but simply the air going quiet, the oxygen that every animal on the planet runs on, draining back out of the sky because the plants that make it can no longer run their chemistry. The world will still be here when that happens, still turning, still holding its oceans for a while longer, but the breathing part of it will be over, the animal world gone, the planet handed back to the microbes that held it first. The green moment does not end in a bang when the oxygen goes. It ends with a planet that simply stops being able to be breathed, still circling the sun, quietly no longer ours. Set a human life against this, and the scale becomes almost hard to hold. Everything that has ever happened in recorded human history, every nation and every war and every word ever written down, fits into the last several thousand years, which against the billion years of breathing air still ahead, is thinner than the finest line you could draw, and that billion years ahead is itself the closing portion of a window that has already been open for 4 billion. We arrived almost at the end of the lit stretch, near the back of the breathing world's long day, and we have been here for a sliver of it. The Earth did almost all of its living before we showed up, and will do the slow, painful last of its living, the loss of the air and the seas, long after anything like us is gone. We are a brief presence near the end of a brief window. That is the honest position in the timeline, and it is worth feeling the size of it. The loss of the oceans, when it comes, will not be a sudden boil, but a slow bleeding into the sky. As the sun strengthens past the threshold, more and more water vapour rises into the upper atmosphere, where it had always been scarce before. And once it is up there, the sunlight breaks it apart, and the hydrogen escapes to space, a little more in each passing age. The seas do not flash to steam overnight. They thin over millions of years, the shorelines drawing back, the shallow seas going first, the water leaving the planet molecule by molecule through the top of the air until the basins stand empty. It is the same process that emptied Venus, only slower, and the end of it is the same, a world that had oceans and then did not, the water neither frozen nor hidden but gone from the planet entirely, out into space where no later cooling could ever bring it back. The exact figures carry honest uncertainty, and it cuts both ways. Some studies push the end of the biosphere out further, to 1.5 or nearly 2 billion years depending on how they handle the feedbacks. None of this touches the much shorter timescales that actually shape human life, the centuries and millennia we usually worry about. And I am not suggesting anyone needs to feel the heat of a brighter sun on their own skin, but the direction is not in dispute, and the rough timing is robust across the studies. Earth is late in its window, not early. The breathable air is on its way out, on a clock measured in a small number of billions of years, and the loss of it is the next major act, not some final one waiting at the very end. So the clock is running on Earth, and most of it has already run. But you might be telling yourself that Earth is at least the lucky one, the best case among the worlds out there, and in a little while I am going to show you the most common worlds in the entire galaxy, and why, for most worlds, the window is even shorter than ours, or never really opens at all. The most common worlds in the galaxy have it worse than Earth, not better. When we picture other worlds, we tend to picture more or less Earth-like ones, planets in steady orbits around steady stars, waiting patiently in their habitable zones. The actual statistics of the galaxy do not look like that. The most common kind of star by a wide margin is the red dwarf, a small, dim, cool star far less massive than the Sun, and around 3/4 of all the stars that exist are these. If you want to know what a typical star looks like, you do not look at the Sun, you look at a red dwarf, and the worlds around them face conditions that make Earth's long, comfortable run look like the rare good fortune it probably is. Because a red dwarf is so faint, its habitable zone, the band where a world could hold liquid water, sits very close in. A planet has to huddle near the small red star to get enough warmth for water, often closer to it than Mercury is to the Sun. That closeness brings a problem that has nothing to do with brightness. A world that near to its star is gripped hard by the star's gravity, hard enough that over time its rotation locks. It ends up keeping one face turned permanently toward the star and the other turned permanently away, the way the moon keeps one face always toward Earth. One hemisphere lives in unending daylight, baked without pause. The other lives in unending night, frozen in a darkness the star never touches. The planet does not turn through a day. It simply holds, half in glare and half in dark, forever. And the stars themselves are violent. Red dwarfs, especially while they are young, throw out flares far larger in proportion than anything the sun produces, sudden eruptions that can briefly brighten the star enormously and wash the close-in planets in bursts of radiation. The strongest of these flares can reach something like 1,000 times the strength of the largest flares the sun has ever sent toward Earth, and they fall on worlds that orbit far closer to the star than we do. A barrage like that, repeated over hundreds of millions of years, can strip a planet's atmosphere away into space and scour whatever is left at the surface with radiation. So the single most common kind of world in the galaxy is not a calm blue planet turning gently through its days. It is a tidally locked world, one side seared and one side frozen, pressed up close against a small red star that lashes it with flares. The deck is stacked against it from the start. The 7 worlds of the TRAPPIST-1 system are the nearby example, a single red dwarf with a tight family of rocky planets, several of them in or near the habitable zone, all of them orbiting closer to their star than Mercury orbits the Sun, all of them almost certainly locked, and all of them subject to the star's flares. That one system, close enough that we can study it in some detail, holds more rocky worlds in its habitable zone than the Sun does, and every one of them faces the same hard conditions. Multiply that across the galaxy, across the hundreds of billions of red dwarfs, and you start to see what the typical world is actually up against. This is the place to be most careful, because it is genuinely contested, and I am not going to tell you these worlds are certainly dead. There is real work suggesting the picture might be less grim than it first looks. The flares often erupt from the higher latitudes of the star, nearer its poles, which means they may largely miss a planet orbiting around the star's equator, firing off harmlessly above and below it. And the fear that a tidally locked world would freeze solid on its night side, its air migrating to the dark hemisphere and snowing out, has softened because climate models show that a thick enough atmosphere can move heat from the day side to the night side, well enough to keep the whole planet from freezing over. A tidally locked world, around a calm enough red dwarf, might hold its air and keep liquid water in the ring of permanent twilight between the two faces. We do not know that red dwarf worlds are all dead. What we know is that the most common worlds in the galaxy face the hardest conditions, not the easiest, and that whatever windows they get are bought against tidal locking and a flaring star. The nearest star to the Sun is one of these. Proxima Centauri, just over 4 light-years away, the closest stellar neighbour we have, is a red dwarf, small and dim and cool, and it is a flare star given to sudden violent brightenings. It has a world in its habitable zone, called Proxima b, roughly the mass of Earth, orbiting so close to the little red star that its year is only 11 days long. That world is almost certainly tidally locked, one face held always to the star, and it sits near enough that the star's frequent flares wash over it directly. We do not know whether it has kept an atmosphere, or whether the flares stripped it away long ago. The closest possibly habitable world to Earth, the very first one we would reach for, is a tidally locked planet being flared by a red dwarf, and we cannot yet say whether it is a living world or a dead one. There is a bitter turn in these stars, because in one sense they are the most durable places in the galaxy. A red dwarf burns its fuel so slowly that it can keep shining steadily for many tens of billions of years, far longer than the Sun's 10 billion, longer than the universe has so far existed. A world around a red dwarf, if it could only hold its air and ride out the flares, would have a window measured not in billions of years but in tens of billions, the longest run any world could possibly get. The longest lived stars in existence host the most common worlds in existence, and yet those worlds may be among the least likely ever to come alive at all, locked and scoured and stripped before life could take hold. The galaxy's most patient fires may mostly warm dead worlds. The TRAPPIST-1 system is worth staying on because it shows the pattern in miniature. A single small red star, dimmer and cooler than the sun, with 7 rocky worlds wheeling around it in tight, fast orbits, all of them closer to their star than Mercury is to ours, the outermost finishing its year in less than 3 weeks. Several sit in or near the habitable zone, and all of them are almost certainly tidally locked, each holding one face to the red star and one to the dark. On a world like that, if it holds any air and water at all, the only place that might stay temperate is the ring of permanent twilight running around the planet between the baked day side and the frozen night side, a thin band of unending dusk where the star sits always on the horizon. That narrow ring, on a locked world around a flaring star, is close to the best the most common kind of planet in the galaxy tends to offer. And I keep coming back to how much of this we genuinely do not know yet, because it would be dishonest to hand you the grim version as settled. We have not confirmed that a single one of these red dwarf worlds is dead, nor that a single one is alive. We are still working out whether their atmospheres survive the flares, whether the locking dooms them or merely shapes them, whether the twilight ring could hold liquid water for billions of years. The honest position is that the most common worlds in the galaxy sit under the hardest conditions we know of for life, and that we cannot yet say how many of them those conditions actually kill. What is not in doubt is that the typical world is not a gentle one, but whatever windows these worlds get are bought against a locked sky and a violent star, and many of them surely get no window at all. The worst of the flaring comes early, when a red dwarf is young, and that timing matters because it overlaps with exactly the stretch when a world would be trying to get life started. A young red dwarf can spend hundreds of millions of years or more in a violent phase, flaring hard and often drenching its close-in worlds in radiation and tearing at their atmospheres, during the very period when a planet is settling and any chemistry that might lead toward life would be taking its first fragile steps. A world can be stripped of its air before it ever has a chance to become anything, its window slammed shut before it could open. So for many of these most common worlds, the question is not how their life ended, it is whether the violent youth of their star ever let life begin at all. And the numbers are what make the red dwarfs decisive for the whole picture. There are something like 100 billion or more red dwarfs in this one galaxy, far outnumbering every other kind of star combined, and a good fraction of them carry rocky worlds, many of those in the close-in habitable zone, where the locking and the flaring take hold. So when you ask what the typical world in the galaxy is like, you are mostly asking about these by sheer weight of number. The default world is not Earth, and not even a sun-like star's planet. It is a small rocky world, locked to a dim red star, soaking up flares, holding at best a thin ring of twilight where anything might survive. That is the most common address in the galaxy, repeated billions of times over, and most of those addresses are likely either dead now or were never able to live in the first place. On the best of these locked worlds, the one place that might hold something like a temperate climate is that ring of permanent dusk between the two faces, and it is worth seeing how strange a place it would be. The star sits always on the horizon there, never rising and never setting, casting a long, low red light across the ground in one fixed direction without end. On one side of the ring, the land falls away into the scorched day hemisphere, on the other into the frozen dark, and the narrow strip between them never sees the star climb or fall. Whatever weather such a world had would be driven by the steady flow of heat from the baked side toward the frozen one, hard winds running always the same way. It is not impossible that water could pool and something could hold on in that ring, but it is a thin and pinned down place to make a stand, a sliver of dusk on a world that never turns under a star that flares. So put the whole picture together. The gentler worlds, the ones around stars like the sun, get a real window, but a finite one that the brightening star always closes in the end. The most common worlds, the ones around red dwarfs, face the worst odds of all, and may get a brief window or none at all. Either way, the ending is built in, which leads straight to the question that has been waiting underneath all of this, the one the bookkeeping forces. Across the whole history of the galaxy, with windows opening and closing on world after world, how do the dead worlds and the living ones actually compare in number? The dead outnumber the living, and they always will, by a margin that only grows. You can see why without knowing how often life starts, without counting a single living world, just from the bookkeeping of the windows. A world is alive only during its habitable phase, that brief lit middle stretch. Before it, the world is not yet living. After it, the world is dead. And here is the asymmetry that settles everything. The living phase is temporary, but the dead phase is permanent. A world that loses its window does not get another one. It does not cool back into habitability or refill its lost oceans or rebuild the air that was stripped away. Once a world is dead, it stays dead for as long as it exists. Follow that through across the age of the galaxy. As time passes, world after world enters its window, lives through it, and exits into death. The ones that die do not come back. So the count of dead worlds only ever rises. It never falls. Meanwhile, the living worlds are the ones that happen right now to be inside their windows, and that set is constantly losing members to death, and only sometimes gaining new ones as fresh worlds settle into habitability. The dead pile up without limit. The living flicker on and off, a roughly steady scattering at best, swamped by the growing accumulation of the dead. Run that forward for billions of years, and the ratio is not close. The corpses dominate, more and more completely, the longer the galaxy runs. This holds even if living worlds are common. Suppose habitable zone worlds are everywhere, that there are billions of them across the galaxy, that life gets a foothold readily wherever it can. It does not change the conclusion. Each of those worlds is still alive only for its brief window and dead forever after. So at any given moment, the living ones are a thin slice of all the worlds that have ever been able to hold life, and that slice gets thinner as the dead accumulate behind it. A galaxy generous with life would still be, at any snapshot in time, overwhelmingly a graveyard, simply because death lasts and life does not. Abundance of life and dominance of the dead are not in conflict. Both can be true at once, and the physics says they probably are. So the picture to carry is not a living galaxy with a scattering of dead worlds in it. It is closer to the reverse, a galaxy filling steadily with dead worlds, accumulating them over billions of years into an enormous and permanent population of corpses, lit here and there by the small temporary set of worlds that happen to be passing through their windows at the moment. The dead are the rule and the standing condition. The living are the exception and the passing one. The gardens are real, but they are scattered thinly through a graveyard that is always getting larger, and each garden is on its way to becoming one more grave. I want to be honest about what kind of claim this is, because it is not a head count. We have directly confirmed exactly one living world, the one underfoot, and we cannot yet point a telescope at a distant planet and say with certainty whether anything lives there. So this is not a census of the galaxy. It is an argument from the nature of the windows, from the plain fact that the dead state is permanent and the living state is temporary, and that permanent things accumulate while temporary things do not. You can question the numbers because we do not have them. The logic underneath is much harder to escape. Things that last pile up. Things that pass do not. Death lasts. Life passes. The accumulation has been running for a long time already. The galaxy is more than 13 billion years old enough that whole generations of stars have lived and died and seeded the material for the rocky worlds that came after. For most of that span, worlds have been forming, entering their windows and dying out of them, dropping one after another into the growing population of the dead. We are not near the beginning of this. watching the first worlds wink out. We are deep into it, surrounded by the dead worlds of billions of years of this happening, the corpses of planets that lived and died long before the Earth had finished forming. The graveyard is not starting to fill, it has been filling the whole time, and it was already crowded before we arrived. And it only runs one way from here. Star formation across the galaxy has already passed its peak and is slowly winding down, so fewer new worlds will be built in the future than were built in the past, while the existing ones keep reaching the ends of their windows and dying. The set of living worlds will thin as the galaxy ages, not thicken. Run the clock far enough forward, and you reach a galaxy that is almost entirely dead worlds, cold and lightless, the living ones grown rare to the edge of absence, the last few windows closing with nothing opening to take their place. The era we live in, with the galaxy still bright with young stars and some worlds still passing through their windows, is itself a kind of window, a comparatively lit early stretch in a future that only grows darker and emptier from here. There is a quiet consequence of all this, for the old question of why we have never heard from anyone. If living worlds are not only rare but brief, lit for a thin slice of their existence and dead forever after, then even if life arises often, the chance that two living worlds overlap in time, close enough and alive at the same moment to ever find each other, grows small. The windows do not only have to open, they have to open near one another, and at the same time, out of billions of years in which they could fall anywhere. A galaxy could have produced life many times over, and still be silent now, simply because the living moments are scattered too thinly through time to coincide. The graveyard does not only outnumber the living, it separates them, holding the rare lit windows far apart in time as much as in space. And the trend has a direction that does not reverse. The bright era of the galaxy, full of young hot stars and freshly made worlds, is a phase, and it is passing. Star formation is winding down, the gas that makes new stars is being used up, and the long future belongs to dimming and cooling and the slow exhaustion of everything that burns. The dead worlds will keep accumulating while the living ones grow rarer, until the galaxy is a dark field of corpses around faded stars, with life either gone entirely or clinging on in some last few places we can barely picture. We happen to be alive not only in the lit window of a world, but in the lit era of a galaxy, an early bright stretch that the future does not get back. The darkness is not only around us in space, it is ahead of us in time, and it is where all of it is slowly going. Hold on to the asymmetry, because it is the whole engine of the conclusion. Almost every other count in nature can go up and down. Populations rise and fall, stars form and fade, worlds heat and cool, but the count of dead worlds only rises, because death, for a world, is the one change that does not reverse. A frozen world does not thaw back to life on its own. A world stripped of its air does not rebuild it. A world that lost its water to a runaway does not get the water back. So while nearly everything else in the universe cycles, the population of the dead does not. It ratchets, one direction only, climbing with every window that closes and never falling, until the dead are not merely the majority but the overwhelming and permanent condition of nearly everything the universe has ever made capable of life. It helps to separate two questions that get tangled together. One is how many worlds are alive right now, in this moment, across the galaxy. The other is how many worlds have ever been alive at any point in the galaxy's history. The first number, the living right now, might be small or might be large, and we genuinely cannot say. But the second number, every world that has ever held life across all of cosmic time, is a tally that only grows, and every one of those worlds, except the few currently lit, is now dead. So however you answer the question of the living present, the dead past dwarfs it, because the past is where almost all the windows are, opened and closed long ago, their worlds gone quiet. The living are a thin slice of the present, the dead are very nearly the whole of history. And there is a strange wrinkle in even trying to count the living worlds, which is that we never see any distant world as it is now. The light from another star takes years or centuries or many thousands of years to reach us, so every world we could ever study we see as it was when that light left it, not as it is today. A world that looks alive in the light reaching us now might already have closed its window in the time that light was crossing the gap. A world that looks dead might since have come into one. We are always looking at the past out there, never the present, which means the living and the dead are not only separated across space and time, but blurred together in what reaches us, the light of windows that may have shut long before it ever arrived. The galaxy we see is a record of what was, lit in part by stars that are themselves already gone. And if the living worlds are this rare against the dead, and each living world holds its life only briefly, then it is worth turning the same hard look onto life itself, even where it succeeds. Not how many worlds are alive, but what being alive amounts to, measured honestly against the whole long existence of a world that manages it. Because the brevity does not stop at the scale of the galaxy, it runs all the way down into the single living world we actually know. Even on a world that does live, life is a thin film and a brief one. Take the one example we have. Earth is a ball of rock and metal about 13,000 kilometers across, dead stone almost all the way through, a hot interior of churning metal wrapped in thousands of kilometers of solid rock. The living part of it, every organism that has ever existed, is a skin on the outer surface, a layer of green and breathing things that reaches only a little way up into the air and a little way down into the soil and the sea. Measured against the size of the planet, the entire living world is a film almost too thin to draw to scale, a faint smear on the outside of a dead sphere. That is what a living world actually is, even at its most alive. Not a living planet, but a planet with a living film on it. And the film is temporary, even here, even on the world that worked. Complex life, anything larger and more organized than a single cell, has existed on Earth for only the last several 100 million years, out of a history more than 4 billion years long. For most of the time Earth has been alive, the most advanced thing on it was a microbe. The breathing, moving, complex world is a late and short development, and as we have already seen, the oxygen that supports it has only about another billion years to run before it collapses. When that window closes, the film will thin and fade. The complex life will go first, then the rest, until the surface is bare again, and the planet will continue, dead, for billions of years more. Earth will spend far longer as a corpse than it ever spent as a living world. When a world dies, it keeps almost nothing of having lived. Whatever the planet was, whatever grew or moved or breathed on its surface, leaves strikingly little behind once the window closes and the surface is stripped and baked or frozen. Mars is the test case, sitting right next door. If life ever did get a foothold there in its wet early years, and we genuinely do not know whether it did, it left nothing we have yet been able to confirm, no clear mark on the dead planet that survived the billions of years since. A dead world does not advertise its living past. It mostly erases it. The riverbeds survived on Mars because they were carved into rock on a large scale, but the question of whether anything lived in those rivers may have no readable answer left at all. So life is not a sturdy, permanent thing that takes hold of a world and keeps it. It is a thin, transient film that appears, where it appears at all, for a fraction of a world's existence, and then vanishes, leaving little trace. It is not the rule that occasionally fails to hold. It is the rare exception that always, in the end, ends. Across the existence of any world that manages it, the living stretch is a thin, bright band in the middle of a long darkness before and a longer darkness after, and the darkness is the normal condition, the light is the anomaly. The one honest caveat is about how often the light comes on at all, and it runs the other way from everything else. We have a sample of exactly one world that we know came alive, so we genuinely cannot say how common or how rare the spark is. Life might be frequent across the galaxy, igniting readily wherever a window opens, or it might be so rare that living worlds are scattered almost unimaginably far apart. We do not know, and anyone who tells you they do is guessing. What this section is about is not how often life starts, it is how long it lasts once it does, and the answer to that, drawn from the one case we can actually read, is not long, briefly, thinly, and then not at all. Put numbers to the thinness and it gets starker still. The whole living world, every organism on Earth combined, weighs almost nothing against the planet that carries it, a layer of living matter that is a tiny fraction of 1% of the mass of the rock beneath. The film of life reaches a few kilometers up into the air and a few kilometers down into the crust and the sea, a shell thinner, in proportion, than the skin on a piece of fruit. And it is the only such shell we have ever confirmed anywhere at all. Everything we know to be alive lives in that one thin layer, on that one world, inside that one window, against the size of just this single planet, let alone everything beyond it. Life is a faint surface tint on a ball of dead stone. And even the record of life is worn away with time. On Earth, the surface is constantly recycled, old rock dragged down and remade, so that the planet has scrubbed away most of the direct trace of its own earliest living past, and we piece that past together from scraps. On a dead world, the erasure runs further. If Mars held life in its wet early years, the billions of years of cold and radiation and grinding dust since may have left nothing we can read, no clear signature in the rock that survived to tell us. A living world keeps a partial record while it lives. A dead world lets even that fade. So the thin film of life is not only brief and rare, it is quietly forgotten by the very worlds that carried it, leaving the dead planets to sit silent, with no clear sign they were ever anything more than stone. You can read the brevity of the living film in the rock of Earth itself. The planet keeps a partial diary in its layers, and for most of the pages there is almost nothing to write but microbes, billions of years of single-celled life, slowly changing the air, building up the oxygen, with nothing larger anywhere. Then, near the very top of the stack, in the most recent thin layers, the complex life appears all at once in geological terms, the animals and the plants, the whole crowded living world, pressed into a sliver at the top of a pile that is mostly empty of it. The breathing world we belong to is not the main story of life on Earth. It is a late, brief flourish at the end of a long quiet, and the rock makes that proportion plain, layer by layer, most of them holding nothing but the faint traces of the simplest things. And almost none of it is built to last once the life is gone. The bodies, the forests, the reefs, the herds, the entire texture of a living world leave only the faintest and most fragile record, most of which is destroyed in time by the same restless geology that keeps a living planet going. Strip the life away and let the planet bake or freeze for a few billion years, and what remains is stone that gives up its living past, only grudgingly, if at all. The dead worlds out there may have held life that vanished without leaving us anything we can read from here. A planet does not carry a sign saying it was once alive. It mostly just goes quiet, and the quiet looks from a distance exactly like a world that was never anything but stone. And here is what gets me about that thin film. It is, so far as we can tell, the only place in all of it where anything matters at all. The dead worlds do not care that they are dead. The empty rock and the stripped air and the frozen poles have no stake in anything. Everything that has ever mattered to anyone, every thought and every loss and every moment of being alive to it, has happened inside that thin film of life, on the lit surface of a world, inside its window. The living film is microscopic against the dead rock, and brief against the long dark, and it is also the entire location of meaning, in the only place we can actually check. The universe is mostly dead, and the small living part is the only part that knows it, the only part for which any of it counts, and that part is the part that always, in the end, goes. Think about what a visitor would actually find if it came through this part of the galaxy and looked. Mostly dead worlds, scorched rock close to the stars, frozen rock far from them, stripped and airless worlds locked to dim red stars, the occasional giant planet with its dead moons. Here and there, rarely, a world in a window, lit and wet and possibly alive, easy to miss against the great number of corpses. If the visitor came through at the wrong time, a few 100 million years early or late for any given world, it would find even the living ones either not yet started or already finished, dead rock where a window had been or would one day be. The living worlds are not only rare in space, they are hard to catch in time. A survey of the galaxy is mostly a survey of graves, with the rare garden easy to pass right over. Everything I have said about how long life lasts rests on a single example, and it is worth being plain about how thin that is. We have one world we know came alive, one biosphere we can study, one history of life to read, and from that single case we are trying to reason about all the rest. It is the narrowest possible base for any claim. Maybe Earth is typical, and life everywhere runs the same brief course. Maybe Earth is strange in ways we cannot see from inside it, and life elsewhere lasts longer, or shorter, or takes forms we would not know to look for. We do not have the second example that would let us tell. So the honest frame for all of this is that it is the pattern visible from one data point and a great deal of physics offered as the best reading available and not as a settled count. The one thing the single example shows beyond any doubt is that a living world can lose its life because ours is going to. Which brings the whole thing back around to the world under your feet and forces the question the rest of this has been circling. If life is a thin film that always fades, if death is permanent and the dead always outnumber the living, if every world gets only a window and then loses it, then what exactly is the Earth right now? Not what we would like it to be, what it actually is, placed honestly against everything the dead worlds have to teach. Earth is not the exception to any of this. It is one of the dead worlds, caught early. That is the honest placement, and it is worth stating without softening it. The Earth is a world inside its habitable window, with most of that window already spent, travelling the same road that Mars and Venus travelled, toward the same destination, only on a slightly later schedule and by a slightly different route. The difference between the living Earth and the dead worlds beside it is real, but it is not a difference of kind, it is a difference of timing. We are not a separate category from Mars and Venus. We are the same kind of thing, at an earlier point on the same path. Hold the three of them side by side, because together they tell one story rather than three. Venus was the right size and kept its heat in its air, and the brightening sun pushed it past the inner edge, and the runaway emptied it. Mars was too small, lost its heat in its shield and its air, and froze. Both of them, early on, were worlds with a real chance, worlds with water, the kind of place where, looking at them then, you might have picked any of the three as the one most likely to last. Each reached the end of its own window first, by its own death, and went quiet. Earth is the one still inside its window, still lit, still green, and from inside it that feels like being the winner. It is not being the winner, it is being earlier in the same sequence. And the end of Earth's window is not in doubt, only its exact date. The oceans that cover most of this planet will evaporate as the sun grows stronger, the same way Venus lost its seas. The breathing air will go before that. On its shorter clock, the green film will fade, the surface will scorch and dry, and what is left will be a hot, bare world circling a swollen sun, its ocean basins empty, its rivers reduced to dry channels carved into the rock with nothing left to run through them. That is not a strange or unlucky fate for Earth. It is the ordinary fate of a world, the one Mars and Venus already reached, the one every world in every closing window is headed for. We are not watching the deaths of other worlds from a safe place outside the pattern. We are inside the pattern, in the lit part of it, near the end of our turn. I think the hardest thing to hold here is how complete the illusion of permanence is from the inside. Standing on a living world, in the middle of its window, the green and the water and the breathable air feel like the fixed background of reality, the way things simply are and have always been and will always be. They are not the background, they are the event, the brief unusual stretch, the anomaly between the long dead beginning and the long dead end. Every living thing that has ever existed has lived inside one of these windows, on one of these worlds, in the lit middle, and every one of them, if it could think about it at all, would have felt the same false sense that the light was permanent. It never was on any of them. It is not here either. The illusion is total from the inside, and that is the part one keep turning over. Nothing in ordinary experience tells you the ground is temporary. The sky holds steady. The seasons come around. The oceans stay where they are, generation after generation. And every instinct built into a living thing reads that steadiness as the permanent shape of the world. No creature that ever lived on Earth could feel its window closing, because the window closes on a scale no life can perceive, billions of years wide, while a life lasts a flicker. The permanence is not real. It is only that the change is too slow and too large for anything living inside it to see. We are the first thing on this world able to work out, from the rock and the physics, that the steadiness is an illusion, and even knowing it, we cannot feel it. The window still feels like forever from in here. So that is the honest placement of the Earth, set against everything the dead worlds show, not the secure exception, not the world that beat the odds for good, but one more world in the lit middle of its window, early in the same sequence that has already ended Mars and Venus, and will end this one too. We are alive in the brief green moment of a world that will go dark, the same way countless worlds have gone dark before it, and countless more will after. And when I try to hold all of that in mind at once, the place it keeps bringing me back to is not some distant planet around another star. It is the ground next door, on Mars, where the rivers used to run. There is a way in which this is the oldest fact there is, only written at the scale of worlds. Everything that lives, lives in a window. A life has a beginning it did not feel, and an end it moves toward. A lit stretch in the middle that is the only part it ever knows, and from inside that stretch the living tend to treat it as the whole of reality, because it is the only reality they are given. Worlds are no different, only slower and larger. The Earth is in the middle of its window the way a living thing is in the middle of its life, carrying on as though the lit part were permanent, when the lit part is exactly the thing that ends. I do not find that thought comforting, but I do find it clarifying. We are not standing outside the pattern looking in. We are inside it, the way everything alive always has been. So when people ask whether the Earth is special, I think the honest answer is yes and no, and the no is the part we tend to skip. Earth is special in the way every living window is special, rare and brief and lit against a long dark. It is not special in being exempt. It will end the way the others ended, by the same kinds of death, on the same kind of clock, and the dead worlds we look out at are not a different category of thing, but a glimpse of where this one is going. That is what the riverbeds on Mars have come to mean to me, the more time I have spent with all of it, and it is where this leaves me when I try to say plainly what the whole thing adds up to. I have gone looking, while putting this together, for the turn that would make it lighter. The fact I could end on that would take the weight off, and I have not found one that is honest. I could tell you that life might be more common than the grim version suggests, and it might be, but that does not change that every instance of it ends. I could tell you 1 billion years is a long time, and it is, but it is still a finite count with most of ours already spent. The honest shape of this does not bend toward comfort, it bends toward clarity, which is a different and harder thing. The Earth is a living world in the lit part of its window, and that is precious exactly because it is temporary, not in spite of it. And the one thing the dead worlds ask of us is that we see clearly what kind of thing we are standing on, and how rare and how brief the standing is. The more time I have spent with all of this, the more the dead worlds have started to look less like other places and more like a mirror. Mars is what happens when a world too small loses its heat and its air. Venus is what happens when a world the right size sits a little too close and the heat runs away. Both of them were once worlds with water and a real chance, and both are where they are now because the same processes working on Earth worked on them first, or faster, or under worse conditions. When I look at Mars, I am not looking at an alien curiosity. I am looking at one of the ways this ends. When I look at Venus, I am looking at the other. The dead worlds are not a separate subject from the Earth. They are the Earth's own future, laid out in two directions, already reached by the worlds that got there ahead of us. And that, in the end, is why a long look at dead worlds keeps turning back toward this one. The point of studying the corpses is not the corpses. It is to see clearly at last what the living world actually is, stripped of the comforting sense that it is permanent. A world that can hold life, holds it briefly, and then loses it, and fills the dark with far more dead worlds than living ones. And the Earth is not the exception to that, but an example of it. Caught early, still lit, still ours for a while longer. That is the whole of it, as plainly as I can put it. And when I try to find the single image that holds it, I do not reach for anything far away. I reach for the closest dead world there is, and the rivers that used to run on it. I do not think the right response to any of this is despair, and I have tried not to write it that way. The window being brief is the reason the lit part is worth anything at all, a thing that lasted forever, that could never be lost, would not be precious in the way a living world is precious, here for a while and then not. The dead worlds do not make the living one meaningless. If anything, they do the opposite, by showing how rare and how temporary the living state actually is, how much had to fall right, and how briefly it holds. Knowing that Earth is early in its ending does not make the green moment smaller. It makes it the only thing of its kind we have ever found, lit now, ours now, for a stretch that is long by any human measure, and brief by the only measure that finally counts. This is not despair, and it is not a trick to make you feel small, and I want to be clear about that. It is just the measurement carried out honestly to its end and then faced. A world holds life for a window and then loses it. The dead outnumber the living and always will. Life is a thin film that fades, and the Earth is one world among those not exempt from the rule but subject to it, early in its own ending rather than safe from one. Early is not the same as exempt. It only means there is still time left on the clock. Not that the clock is not running. The clock is running. It has been the whole time, and most of it has already gone. I keep coming back to those dry riverbeds on Mars. Water ran there once, under a sky that has since been stripped away, and now the channels sit empty in the cold, the record of a world that had its time and lost it. When I started looking into this, I thought of the dead worlds as the failures, the ones that never got going, while the Earth was the success, the one that worked. I do not think that anymore. What I have come to see is that a living world is not a kind of world at all. It is a stage a world passes through, briefly, on its way to being dead, and every world that has ever held life is either in that stage right now or already out the far side of it. Mars passed through it and lost it to the cold. Venus passed through it, if it ever really began, and lost it to the heat. And the Earth is passing through it right now, with most of its window already behind it. The oxygen we breathe on a clock that runs out in about 1 billion years. The the oceans on a longer clock that ends with them boiling away into a sky gone strange. We are not the exception to the graveyard. We are one more world in the middle of its brief green moment, mistaking that moment for the permanent state of things. The dead worlds were not always dead. They were once exactly where we are, and one day the rivers here will be dry beds too, carved into the rock, frozen in place, waiting for nobody. If you want to keep looking at the worlds out there as they really are, a subscribe keeps the next one close, and you are welcome here any night.